Okay, so let's go on to the next chapter, which is chapter 14. So we're gonna be looking at chapter 14 now on metals. Okay, metals is quite a big chapter because there's quite a lot of segments within it. I guess to know how to really study this chapter, you should know how the different segments are linked up together. So let's start off with the first part, metal and alloys. So under chapter 14.1, okay, what actually is happening here is that we are going to look at the properties of metal, okay? And that's really the key thing here. We're going to look at the properties of metal and why do they behave in that manner. So first thing, the general properties, by now most of you should know. They are good conductors of electricity, good conductors of heat. They have high densities together with melting and boiling point. You realize these 3 points are linked up together. Next one, they are malleable and ductile. So malleable and ductile is also together. So take note. Now, my suggestion would be this, instead of listing them as 4 different points, is to link it up as 3 different points. So these 2 together, point 1. This itself is point 2. This is point 3. Okay, so these 3 points over here are the general properties of metals, and the explanation itself also will follow accordingly. Okay, now, before we even go into the description of each of the properties itself, you realize that, oh, they talk about why pure metals are not used widely in industry. Okay, so pure metal, the opposite is actually the alloy. So that means they are mixed with other things. So they want to talk about pure metals over here first, so that later on when they talk about alloys, it's easier for everyone to understand. So first up, let's look at pure metals. So pure metals, generally, they are soft. Okay, if they are soft, this means that they're not hard. What does it mean by they are not hard? So in the concept, when you look at a microscope, when you go all the way down to the atom level, you realize that atoms are packed regularly in layers if they are pure. Right? In pure metals, they are packed regularly in layers, as what you can see over here in this diagram. Okay, so this is the point A, packed regularly in layer. So if I apply a force, what you realize is that because they are so regular, when I apply a force, okay, they can actually slide over one another easily, which is seen over here, because of the regular arrangement. So the key idea here is the regular arrangement causes the sliding over one another easily. Okay, so this is the key idea why they are soft. Regular arrangement, you apply a force, they will slide over each other easily. Next thing, pure metals may react with air and water and wear or corrode away easily. Okay, this one later on we'll go through, but sometimes pure metals may not be that good because you want to maintain your metal, you want to make sure that the metal can last long. So you may want to mix it with other things so that it doesn't react with air and water that easily. Okay, maybe you don't even want it to corrode or wear away. So therefore, because of these 2 reasons, generally alloys are used. Okay, so later on you'll see alloys is a mixture. Sorry, let me scroll up. It's a mixture, okay, of other elements with metals. Okay. Now, next one, alloys. Okay, oops, I just mentioned it. Okay, so alloys mixture of metals with one or a few other elements. Generally, the things around us are mainly alloys. Okay, so metals are often used as alloys. These are the 4 main big reasons you need to take note of this. Okay, first is to make it harder and stronger. So example is brass. All your instruments, typically your wind instruments, are made of brass so that they're harder and stronger. Next thing, okay, they can be used to improve appearance of the metal itself. So pewter, this is actually an alloy of tin, antimony, and copper. Would they ask what's the possible mixture of metals that form pewter? Maybe, okay, too bad you're pure, so more content for you all. So please go and remember this. Okay, so pewter possibly, okay, could be tested in terms of what is the makeup of it. But it is used really to improve the appearance of metals. So those shiny metals, right, is really because of the idea that tin is mixed within it. So you're able to see that shine, that glow. Okay. Next, actually by mixing metals or mixing different metals together, you could lower the melting point of metals. Now, by lowering the melting point, it means that I need to use lesser heat to cause it to melt. to change its shape, to change its shape, so that I'm able to do things with it. So one very key example is actually solder. Okay, solder is actually an alloy of tin and lead. Being able to lower the melting point of it, this actually allows it to be used to join electronic parts on the circuit board. So those of you who got spoiled one, please don't go and open up your current used one. Okay, those that got spoiled one, you can open up, you realize that the circuit board has all these silvery parts, silvery circle that attaches the joints to it, that joins the components together. That's actually your solder. Okay, and last one, okay, metals are often used as alloys really to make the metal more resistant to corrosion. So cupronickel, okay, alloy of copper and nickel used to make coins. So our old coins, the older coins are actually made of copper and nickel. Okay, now, one interesting fact is that your newer coins, you realize they're actually magnetic. Copper, nickel, the old coins, right? Actually, you realize they are not. You try to use your magnet, put it near there. Okay, they are not magnetic. But with the newer coins, actually there's a change in the composition itself already. Okay, what is the composition itself? You can go and find out. I will not tell you because I myself also need to find out. Okay, next. Why are alloys stronger than constituent metals? So what they're trying to do is they're just going to elaborate on this point. Okay, you realize there are 4 benefits of metals being used as alloy, but the main one that they will elaborate further is actually on this. So point 1 is actually elaborate further. So that's why they talk about this, right? To elaborate why are metals used as alloys. We just now went through pure metals have regular arrangement, but in alloys, what happened? In alloys, because the atoms are of different sizes, okay, different metals have different sizes. So the keyword here is actually different sizes. And because they have different sizes, what do you realize? The regular arrangement is actually disrupted. Look at the diagram here. Okay, so this part here shows you, hey, the atoms are no longer arranged regularly. So since they're not arranged regularly, what happens now? If I apply a force, will there be atoms that slide over one another easily? Answer is no. So therefore, because they are of different sizes, the arrangement is disrupted. Okay, they now cannot slide over one another easily when the force is applied. So since they cannot slide over one another easily, therefore they are now considered harder. Because when you hammer, the shape doesn't change that easily. Okay, shape doesn't change that easily. Shape of metal doesn't change that easily. Okay, so I hope you have a better appreciation of why alloys are being used instead of pure metals. Okay, so this is the general question that come out. Why are alloys typically used using, then try to explain it. Okay, so this is the point that you must take note. Okay, now then the question is, should I talk about the pure metal part? Answer is, okay, yes. So this part over here, this whole thing over here, okay, this whole segment here, plus this segment over here, okay, combined together are typically used to explain why alloys are used instead of pure metals, okay, in terms of to make it harder. Okay, so you must explain about the pure part first, then you talk about the alloy part. Okay, so this is this part over here. Okay, this is the composition. Okay, so you can take note of this. So if they ever want to ask you what's the composition of the alloy, it will only be within here. Okay, it will only be within here. So science bites over here, this is an interesting fact. Olympic medals are actually alloys also. Okay, it is the gold medal is actually 92.5% silver, with a thin layer of gold. So although it looks gold, actually your Olympic medal is not gold. It's actually mainly silver. Okay, so cheat code, cheat code. Okay, so that's for 14.1, really looking at the properties of the metal and then looking into the atom level. Why is it so in terms of the hardness of alloys? Right? Okay, 14.2. We're going to go into the reactivity. Key idea. What we are going to do at 14.2 is to find out what the reactivity series. I know most teachers will tell you, okay, let's start off 14.2. This is the reactivity series. Let's memorize it. In actual fact, 14.2 is to help you understand why the metals are arranged as such. So let's go from find out what the reactivity series are. Okay, so how do they actually find out which metal is more reactive, which metal is not as reactive as the others? So what they do is they let the metal react with this either cold water, steam, or hydrochloric acid. So by letting the metals react with these three different chemicals, okay, substances, they actually are able to determine which metal is the most reactive, which metal is the least reactive. Okay. Now, so before we jump into the reactivity, okay, this is actually what happens when the metal react cold water, metal react steam, plus metal react with acid. Okay, later on, metal react acid. So first things first, in terms of cold water and steam, what's the difference? You say, sure, isn't steam and water the same thing? Cold water, we're actually looking at water in the liquid form. Steam, we're actually looking at water in the gaseous form. So this is actually H2O liquid. This is actually H2O gas. Then some of you may say, sure, isn't it the same thing? Since it's reacting with water, what's the difference in terms of the state? Why would the state make a difference? I want you to see in terms of the product. If you let metal react with cold water in the liquid form, okay, water in the liquid form, you will realize that you will get hydrogen plus metal hydroxide. Metal hydroxide. Whereas if I let the metal react with steam, my product is different. Instead of hydroxide, now it's only oxide. So there is a difference in terms of the product when you let the metal react with cold water or when you let the metal react with steam. Okay. So let's go on next to take a look at the table over here. Okay, so this is actually the setup. I think sometimes you will see this in your questions. So actually, how do they make the metal react with steam? So you realize down here, they got glass wool soaked in water. The water is not in contact with the metal. What they'll do next, they will actually heat up the metal. And as they heat up the metal itself, the test tube, actually the water here will start to become steam. It will boil and become steam. And the steam will actually pass through the metal. Right? The steam will actually pass through the metal. And as the steam passes through the metal reacts to steam. Okay? So this is the setup on how they make the liquid water become steam to react with your metal. Okay? For practical wise, okay, this is actually more for your practical. So do take note to prevent water from being sucked back into the hot test tube. Okay, why would the water be sucked back, right? It's really because when you stop the experiment, the test tube will actually cool down and hence the air will contract and hence there will be a suck back. So what they'll normally do is before you immediately after you switch it off, you'll try to remove the delivery tube so that there won't be a suck back. Okay, the problem with the suck back is this. Can you imagine you heat up the metal, you heat up the whole test tube. Okay, it's very, very hot. When there's a suck back, the liquid water actually flows back into the tube, it goes back in. Water is cooler, the whole test tube is very hot. When the water goes back in, what's going to happen? Okay, you realize that your test tube may crack. And hence we want to avoid such situation. That's why we do not want the suck back to happen. Okay, this is the main reason of why they tell you the caution. Okay, so going back to this, we talked about what metal react with cold water, just throw the metal in. How to show metal react steam, we went through this setup. Then of course, next part is, sure, so what if I know how they react? Okay, so what if I know the product? The key here is we are not really looking at the product itself to determine the reactivity. We are looking at how violent the reaction is or how slow the reaction is to determine how reactive it is. So let's ignore the second column first. Let's look at the first column. Okay, cold water. So what you realize that when potassium reacts with cold water, you look at this keyword here, potassium actually reacts very violently. Okay, what's the next part? Enough heat is produced to cause hydrogen to catch fire and explode. When you hear this, you know that, oh, this reaction must be very vigorous, must be very, very reactive. Okay, compared to sodium, what do you realize was the word that they used that's different? Instead of very violently, they use that sodium reacts violently to form sodium hydroxide. Okay. Down here, put enough heat is produced. For potassium, it says enough heat is produced to cause hydrogen gas to catch fire and explode. What do you realize in terms of the phrasing here? Hydrogen gas may catch fire and explode. You realize there's a little bit in terms of the toning down of the reaction. Therefore, you can straight away deduce that potassium is definitely more reactive than sodium. Okay. Next one, calcium. Oh, the phrasing changed again. Instead of violently, now they change it to readily. Okay, and what do you realize? There's nothing about hydrogen catching on fire now. So the heat produced, okay, it's not enough to let the hydrogen gas catch fire. And lastly, magnesium. Out of the metals that they are testing, magnesium actually reacts very slowly with cold water. Okay, even worse, they want to show you how slow it is, right? Because it's so slow, they say a test tube of hydrogen gas is produced only after a few days. This actually elaborates on how slow it is. However, please don't need to memorize this. Don't need to memorize this. Don't need to memorize this. Okay, don't waste your memory space. Don't memorize this. Okay, there's no need. You tell me react very slowly, I understand, right? Yes, it's going to be very, very slow. So these four metals, okay, obviously will be your key champions here because they all react with cold water. How about the rest of the metals here? Because there's no reaction that occurred, okay, for zinc, iron, and lead, copper, and silver, because there's no reaction that occurred, we can safely say these metals here, okay, from here and below, right, actually, they are definitely less reactive than my top four champions over here, potassium, sodium, calcium, magnesium. Differentiate between the first four with the rest. Now, next one, what they did was they reacted with steam. Okay, steam is actually water that's hotter, right? So it has more energy. So you expect for steam, it's actually a more reactive reactant. Okay, it's actually a more reactive reactant compared to water. Okay, it is actually a more reactive reactant compared to water, compared to cold water. So it's not surprising why the first four, I just straight away write that it reacts explosively. Okay, I've already differentiated them using the first three, sorry. I've already differentiated them using cold water. So when you do this in the lab, actually it's quite dangerous, I gotta say. So typically we will not use steam to react with any of the potassium, sodium, and calcium in the lab. They even say should not be carried out in the school lab, so take note of it. How about magnesium and the rest? So you realize, oh, sure, magnesium this time around reacts violently. Okay, previously it was very slowly with cold water. You can see on the left hand in the second column, but now it is reacting violently with steam. Okay, violently with steam. Now I need you to take note. If ever, okay, you're asked to describe how magnesium reacts with steam, you are expected to know how to write this. Okay. Not just in terms of the product, the white solid form, you're also expected to know that a white, bright glow is going to happen. Okay, a white, bright glow is going to happen. So do take note of this. In terms of zinc, you realize A is less reactive than magnesium. Why? Because it only reacts readily. Hot magnesium is violently, hot zinc is only readily. Okay? Now, I want to put blue here. Okay, this one I put in blue here. This is a star for your practical. Okay, theory, yes, also, but this is a star for practical. Because zinc oxide is an interesting one. When it's hot, it is yellow. When it's cold, it is white. Most people will think that, sure, with this color change, most probably there are two different things. There are two, when it's hot, it's actually a different chemical substance compared to when it's cold. But zinc oxide is interesting itself because it produces different colors at the different temperatures. Okay, in practical, if you're able to observe this, it's bonus points because you know this is a very signature trait, signature characteristic of zinc oxide. Okay, so zinc oxide, need you to take note of it. Okay. Next one, iron. Okay, iron actually reacts with steam, but you can see it's slowly with steam. And since it reacts slowly with steam, we can safely say that this is less reactive than zinc. iron is definitely less reactive than magnesium. So based on the observations, I can now classify that magnesium must be above zinc, zinc must be above iron in terms of reactivity. So what you have done is to differentiate between potassium all the way to iron, okay, when I let it react with cold water and when I let it react with steam. Okay, so that's actually what's happening in this chapter here. You are trying to find out, based on the observations of the reactions, how to rank them in terms of the most reactive all the way to the least reactive. So once again, my lead, copper, and silver, there's no reaction. Okay, there's no reaction. So how to differentiate then these three? Okay, so we go on to the even more extreme measure. So instead of cold water, instead of steam, now we use dilute hydrochloric acid. Okay, it's an even stronger, okay, it's an even stronger reactant. So what's the reaction generally? You put a metal of the acid, you actually get a salt and then get a hydrogen. Now do take note, because you use hydrochloric acid, you get a chloride. Now, if you use a sulfuric acid, okay, to react with the metal, you would normally get something sulfate. So you'll get a sulfate salt. If I use nitric acid, which is another one of your common acids that you will use, you will get something nitrate. So the reaction of the metal with each of the different acids, it will give you a different salt. So you must be able to think of it. Not every single thing is chloride, please. Or only when you use hydrochloric acid, then you get your chloride. I think by now most of you should know, yeah? Okay, so in terms of the reaction of acids, you realize the observation is as such. So potassium reacts explosively, sodium also explosively. That's why they say don't carry out. Calcium reacts violently, magnesium rapidly, zinc moderately fast. So you can see a gradation here, or it gets less and less violent. Okay, it gets slower. Iron reacts slowly. They say, just stuck again, at iron, stuck again. Then how? How do I know the three? So what you realize that, hey, down here got one star here, right? So actually lead can react with hydrochloric acid. Lead can. Okay, but okay, why it doesn't happen is really because there's this insoluble layer of lead 2 chloride that's formed. This is an example that I gave previously in the lesson itself. I'm just going to show it again. So if this is hydrochloric acid, okay, I'm just going to write in the symbol, so save a bit of time. If this is HCl, okay, this is a piece of lead over here. This is Pb, lead. When I let them react, what's going to happen is that the surface is the one, okay, first thing first, the surface is actually the one that's reacting first. Okay, so Pb at the surface of this part over here will react with HCl. When it reacts with HCl, it will form PbCl2, your lead 2 chloride. And this solid is insoluble. Okay, so can you imagine, it's like as you react, there's a layer that protects, okay, don't use the word protect, but that covers lead, okay, from the HCl, and hence it will stop reacting. So what you need to do, if you want it to continue to react, you must scrape off the PbCl2, and then, yeah, it's just a repeated process and must keep doing. And hence, that's why they put a star over here telling you lead normally should, but in this case, it didn't, okay? It didn't appear. So take note, it does not appear, okay, to react. So it does react, but when you look at it, it looks like it doesn't react. So based on all the things that I've gone through so far, okay, this is actually the reactivity series. Now do take note, okay, they put one star here. Note that hydrogen is included in the series even though it's not a metal. Okay, so hydrogen is included here. So this is the series that you must remember. Okay, this is the series you must remember. Now there's one additional element I want to add in also, which is over here. Okay, I want you to, in between here, okay, do take note, have the idea that carbon is over here. So yeah, it's ugly handwriting. Let me rewrite. So carbon is actually over here, right? Why is it important to know the position of carbon? Later on we'll go through it. So, but carbon is actually over there. Okay, but based on the whole reaction, you can determine all of this. Why hydrogen could be inserted here is really because of the reaction with hydrogen, which we'll go through a little bit later on why is it so we are able to determine this. Can? Okay, so take note, in case some of you still haven't memorized the thing. So there's this mnemonic that you can use to go and memorize it. So please send camel, monkey, zebra in large heavy crates soon. I do not know what your teacher may have mentioned to you, okay, but there are different ways to remember the reactivity series. Right, but take note, you should remember them. Okay, so we are done with the reactivity series. So we have now determined which element is the most reactive, all the way down to the least reactive element. So how can we use the reactivity series? Okay, how can we use the reactivity series? Now, so the first one we're gonna look at is that okay, we're gonna look at how we can use it based on these 5 points over here. Okay, we can actually use it in terms of displacement reaction. We're gonna look at how it reacts between a metal and the oxide of another metal. There's also the reduction of metal oxides with carbon, metal oxides with hydrogen, and lastly, in terms of you heating the metal carbonate itself. Okay, so there are total five main ones that we're going through in this next segment. Okay, displacement reaction of metals. Now, the key idea here is the more reactive metal can displace a less reactive metal from a salt solution. Okay, so I want you to look at this example over here that's illustrated here. Okay, when iron filings are added to a solution of copper 2 sulfate, this was observed. The copper metal is precipitated out. So what you realize, the description of copper metal is that it's a reddish brown metal. Okay, so a reddish brown metal is being described. Okay, but can you see here, copper metal is out as a pink solid when freshly formed. Normally in the lab, you won't be able to see this, okay, because the color is quite hard to see. At the end, most probably, this is the one that you'll commonly see is that it's a reddish brown solid. So copper metal, the feature, how does it look? It's actually normally a pink solid when it's fresh, okay? But if you leave it there for a while, it will typically become a reddish brown solid. Next thing, the solution will turn green. So because of this observation, you know that a reaction has taken place. But what exactly has happened? What exactly has happened is that because iron is more reactive, okay? Iron is more reactive than your copper. So iron actually displaced copper. So the iron actually kicked the copper out, and hence you got iron sulfate and then copper being left alone over here. So this is the idea of displacement. Literally, the metal got kicked out. So in terms of the ionic equation, this is it. Don't need to memorize. If you are very good at forming equations, actually, you don't need to memorize ionic equations. You can just do it on your own. Okay. Now, if they reverse the reaction, you realize that it will not happen because copper is less reactive than iron. Okay, so take note, if you were to put copper in iron 2 sulfate solution, actually there will be no reaction. Okay, so this is actually what they're trying to say here. If you put copper into an iron 2 sulfate solution, okay, there will be no reaction that's going to happen. It is what this part here is trying to say. Okay. Okay, so displacement actually helps you to find out which metal is more reactive, which metal is less reactive. So this table that you see here is like a summary of all the displacement reactions in terms of their observations. Of course, you can go ahead and memorize it if you want, but if you do not want, actually there are some key points you can take from here. Okay, you can take from here. What are some of the key points you can take from here is that copper 2 sulfate solution is typically a blue solution. Okay, this guy here is a colorless solution. This guy here is a colorless solution. How about lead 2 nitrate and iron 2 sulfate? Lead 2 nitrate also colorless. But for iron 2 sulfate, it's actually a green solution. You realize this actually follows quite closely to your salts chapter where you need to test for cation, test for anion. The colors actually are quite similar. Next thing, what other thing can you take note of is this. Okay. Magnesium. Okay, sorry. I say, let me erase this. Zinc is actually a gray deposit. So zinc itself is actually a gray solid. So this guy here is a gray solid. Okay, based on this, what else do you know? If you really look at it, okay, this guy here also is a gray solid that you can pick up from all the various observation. Copper here, as mentioned just now, is a reddish brown solid. Okay, lead itself is a gray solid. Okay, iron, question. Okay, what color? Most of you say, sure, iron reddish brown. Rust is reddish brown, but iron is not. Okay, once again, rust is reddish brown, but actually iron is not. Okay, rust is actually Fe2O3. Iron, okay, I mean it's more complex than that, but generally it is not reddish brown. So what color is iron? It's actually the ones that you see around you. It's actually also your gray solid. So in terms of solid wise, the only one you must actually pay special attention to is copper. Okay, copper metal is reddish brown in nature. So these are some of the things you can take note of in case some of you say, how do I know what color it is? Actually, from this table 14.4, you can pick up on these things over here. Okay, so I tell you, your textbook a lot of things are just like whether you got see or never see only. Okay, next. Now, our metal displacement reactions redox. Okay, this is actually considered a redox reaction. Why is it so? We'll cover this next time. Okay, so this one we'll cover more in terms of the redox chapter. Okay, so cover more in the redox chapter. So no worries about this so far. Okay, so this is for displacement reaction. Okay, this is for displacement reaction. Now, question is, after I've learned about the displacement reaction, how is it normally used in the exams, right? I think exams, test questions, how is it normally used? So key idea here, so yeah, let's go back to this table here. Okay, let's use this box as an example. Let's use this box as an example. What I have is magnesium reacting with zinc sulfate. What I know from my metal reactivity series, metal is more reactive with zinc. That's why zinc is being displaced. So I can actually use the reactivity series to predict reactions, okay, to predict whether displacement is going to occur. How about if I got an unknown? So if I give another example, it could be there's an unknown, okay? The unknown is metal X. So metal X, I let it react with magnesium chloride. Then I say, okay, what I got was XCl2 plus Mg. Okay, XCl2 plus Mg. Then question is, after this, what could be the possible identity? Okay, possible identity of X. So what are the possible identity? You know that since X can displace magnesium, hence X should be a metal that is above magnesium in the reactivity series. So in your metal reactivity series, what are the possible answers? Okay, it could possibly be potassium, it could be sodium, it could be calcium. Okay, now, then some of you say, sure, how can it be potassium and sodium? Those who caught on to this fast, good. Why it cannot be potassium and sodium is really because you look at the formula over here. What do you realize? The ratio is 1 metal to 2, of 1 cation to 2 anion, right? XCl2. You realize for potassium and sodium, they will normally form KCl or NaCl. Therefore, this 2 is out. And hence, what's the possible identity? It'll be calcium. Okay? So this is one way to use the metal displacement. Now, another thing I need you to take note when you're doing displacement reaction is that in the metal displacement reaction, okay, the solution here, yes, we can say, it is a FeSO4, okay, SO4 solution. But whenever we talk about solution, you realize it's a mixture. So I'm not just reacting it with FeSO4, I'm actually reacting it with FeSO4 and water because it's a solution. Okay, because it's a solution. That's why I say, you tell me this for what? So what if I know there's water? What is the significance of knowing that there's water? Now, let's go back to this example that I gave at the top. Let's look at this example. Number one. If X is calcium, do you think calcium is just going to displace magnesium itself? Is the only reaction that's going to occur? Answer is no. Why? Because if you scroll all the way back up, what do you realize about calcium with water? Calcium actually reacts with cold water as well. So when calcium is placed in the solution, there's two reactions that's happening. There is a reaction of calcium and water to give you calcium hydroxide and hydrogen gas. That's the first thing. Another reaction that's occurring is calcium displacing the metal itself, okay, displacing magnesium. So observations can be tricky. So before you start to write down the observations, identify what are the reactions that's happening within it, especially for the chapter of metals. It could be a displacement only, or it could be a displacement together with the reaction with water. So this is the tricky part about this, which then you need a bit more practice to try to get a hang of it. Okay. Okay, reaction between metal and oxide of another metal. This is actually still under displacement. Okay, because you are still kicking the thing out. So a more reactive metal can reduce the oxide of a less reactive metal. The idea of reduce actually also is to displace it. So look at the reaction here. Zinc with copper oxide. What you realize the zinc did was the zinc displaced the copper. That's why you got zinc oxide and copper. And hence, if you understood the displacement reaction at the top just now, this is just another application of displacement. Okay, but the question is, why is this going to happen? It's really because of this explanation here. Right? The ability to form positive ions more readily. I say again, it is, when we say it's more reactive, actually we are looking at its ability to form positive ions more readily. This is the idea of why is it more reactive. Okay, so if you're able to form positive ions more readily, then obviously you'll be more reactive, and hence you're able to displace the other elements, the other metal. Okay. Now, we're going to go into reduction of metal oxides with carbon. Actually, this itself is also a displacement reaction. Okay. Although they say here, the more reactive a metal is, the more difficult it is to reduce its oxide to the metal by carbon. Okay, I want to put two together, this one and this one, reduction of metal oxides with hydrogen. So question is, what's the application of these two, reduction by carbon, reduction by hydrogen? Okay, what you're trying to do is actually for these two methods here, you're trying to extract the metal. Typically, this is used in extraction of the metal. Okay, this is also used in terms of extraction of the metal. So we will let it react with carbon, or we'll let it react with hydrogen to try to extract the metal out. Now let's go to carbon first. Okay, carbon. Which metals will be extractable using carbon? Answer is, go back to your reactivity series. If you go back to your reactivity series, you realize, Mr. Eugene, now I understand why you put your carbon here already. It's because carbon, if it's placed over here, I know that anything below it, anything below this carbon over here, okay, can be reduced by carbon. Okay, that means I can extract all of these things here from the metal ore. Okay, I can extract the pure metal from its ore using carbon. Okay, using the idea of reduction by carbon. Now then, how about hydrogen? Let me use a different color. So you realize hydrogen is placed here, which means that anything that's below hydrogen, I can reduce it. Reduce by hydrogen. That means I can extract this metal from their ore by letting it react with hydrogen. Okay, so that's the key point behind your reduction by hydrogen, reduction by carbon. Now, I want to bring your attention to this hydrogen setup over here. Okay. This setup, you will see it in your exam papers and stuff like this. Okay, you realize when you do practice papers, this setup, you will see it. So please don't be too amused by this, thinking what is this? What is this reaction that's actually happening? Okay, so this is actually trying to pass through dry hydrogen. So this actually, realize fused calcium chloride went through. Okay, this to dry the gas. So you dry the hydrogen, then let it react with the lead. What's happening is that the lead-2 oxide here will actually be reduced by hydrogen. So lead will form. Okay, let's use orange color. So as the hydrogen passes through, okay, you actually have a lead forming. Right, lead will be formed here. Then why must I have a hydrogen gas burning here? Now, if I don't let it burn here, can you imagine the hydrogen gas keeps coming out? Hydrogen gas is a flammable gas. So if you let it leak, a lot of gas coming out here, someone accidentally like do a spark, right? The whole lab is going to explode. Right? So you are trying to expand the unused. Okay? So this is actually trying to remove, let me use a different color. Okay? Trying to react away the unused or unreacted hydrogen gas. Okay, so hopefully this gives you a bit more idea of why the setup is as such. Okay, this is not just anyhow, just go and burn, just go and copy and paste. Actually, there's a reason why this is happening. So this is the whole reaction over here. The last one is action of heat on metal carbonates. So the key point is actually this part over here. The more reactive a metal is, the more difficult it is to decompose its carbonate by heat. So some of you just say, okay, I just memorize, I just memorize. Now, don't memorize, okay? Don't memorize the thing. Key idea here. They will, those that's more reactive, okay? Actually, so the more reactive the metal is, okay, the more stable its carbonate is. Which means that this guy here, this one here means less easily, more difficult to decompose. More difficult to decompose. Therefore, because of this idea, this main concept is broken down into these three main segments. Okay, the first two unaffected by heat. You heat it up, it will never decompose. Why? Because potassium and sodium are your two most reactive metals in your reactivity series. Hence, the carbonate is very reactive. The carbonate is very, very stable. So when you try to heat it, it will not decompose. As simple as that. Whereas from calcium onwards, it's less stable now. So when you heat it up, okay, it can decompose. It will give you a metal oxide. Now then you say, what's the difference between this second row over here, and the third row over here? Okay, so row 1, row 2, row 3. The difference between row 2 and row 3, can you see here, is that row 2, all of them decompose into metal oxides. Whereas for row 3, for silver carbonate, they actually decompose into silver. It's not even an oxide, it's a silver. Okay, so this thing here, you must take note, silver carbonate, when you heat it up, it doesn't form silver oxide. Instead, it forms silver itself. But it shows how much it wants to remain as a metal itself. Okay, so unstable, decompose further. Next. So lastly, using reactivity series, you can deduce the order. So all of this is what we have covered just now already. Examples you can look through. I will not go through the example. You can look through. This is actually quite good to consolidate whatever you picked up from the previous parts. Okay, let's go on next. Oh yeah, extracting metals. So what we have done so far is we have used experiments to determine the reactivity series. From the reactivity series, we sort of like determine what reactions they will take place. But of course, in terms of application wise, why would you want to learn all this? Is in our real lives around us, we do use metals quite a fair bit. We use metals a lot. And when we were to dig the ground, dig into the mines, the metals are generally existing in ores. Okay, they do not come as pure metal itself. Okay, only the super unreactive one, such as your gold and platinum, this one, yes, in pure form. Okay, in pure form. These are gold and platinum is very unreactive, and hence you see them generally unreactive, uncombined with other elements. You see them in a pure form. Okay, in pure form. Okay, but most of the other metals exist in ores, especially iron is in ore, copper is also most of the time in ore. So what can we do, okay, to extract the metal out? Okay, what we want to do is, okay, there are three main stages over here, but in your syllabus, the main one we're really going to dwell into is using the idea of metals, and the idea of using reducing the metal compound to the reducing the metal compound of the metal ore to metal using carbon. So this one example will be your blast furnace. Okay. The next one we're going to look at in terms of electrolysis. So electrolysis also can be used to extract the metals. Now, at this point, I want you to take a look at this. Okay, so question is, when do we use electrolysis? When do we actually use reduction by carbon? So electrolysis are generally used for those above carbon. So you realize all these are above carbon, all these above carbon. Hence, I will tend to use electrolysis because I cannot use carbon to extract it. But why we don't want to use electrolysis for every one of them is really because electrolysis is kind of expensive. Right? Electrolysis is actually quite an expensive process. You're using electricity to pass through the ore. You need to melt it. It's going to be at quite high temperatures. It's going to be more dangerous itself also. Okay, so we typically try not to use electrolysis unless required. Okay? Because industrially, it doesn't make money sense. Okay? Unless it's really required. If can, what they'll normally do is they will extract using the reduction with carbon. Because carbon is available everywhere, and hence we will tend to use this. More abundant. Okay, more abundant. Carbon is more abundant. Okay, and it's cheaper. Then gold, because it's found naturally, you don't really extract. You find gold, people go and dig mines to go and find gold, right? So this one here. So generally, the main extraction method is either electrolysis or reduction by carbon. And we're going to go into the idea of how did we actually extract iron from its ore. Okay, extract iron from its ore. So first thing, okay, the main ore for iron is actually called hematite. Hematite actually contains mainly iron trioxide. So this is Fe2O3. It mixed with other impurities such as sand and clay. The main one that we will look at quite a fair bit is the idea of sand. Sand is actually SiO2. Okay, SiO2. Okay, so what is the main factory? What's the main big thing that we use to extract iron? Is actually called the blast furnace. Okay, so let's now go into this. What exactly happens? Now, I wouldn't start from step 1, step 2, step 3, because this is really looking at the whole industrial process. But the meaning making behind it, I always start from step 3. This is all about extracting the iron. So since I want to extract the iron, actually the most important step is step 3. I will always start from step 3 because this is the main thing I want out of the blast furnace. I want to get the iron out from the iron trioxide. So you realize by reacting iron trioxide with carbon monoxide, okay, the carbon present here actually reduces the iron to form molten iron. Okay, so I say again, this is actually the key step over here. The carbon monoxide actually reduces the iron in the iron trioxide to form your molten iron. This is the key step. Okay, this is the key step. Now, then, of course, the question is, where did the carbon monoxide come from? Our air a lot, man. Our air don't have a lot of carbon monoxide. So we need to spend some time, we need to spend some energy to produce that carbon monoxide. So what exactly happens is in your step 1 and 2. So I want to produce carbon monoxide. That's the key idea here. So let's look at step 1. Okay, the carbon in coke. So coke actually is mainly carbon. Okay, it actually burns in the blast of hot air. In the hot air, the main one that is actually reacting is your oxygen. Okay, to produce carbon dioxide. So first step, the coke will react with the hot air, the oxygen in the hot air to produce carbon dioxide. First step. Now, this is still not what we want. We want carbon monoxide. Hence, we're going to let the carbon dioxide react with the coke further. Okay, we're going to let the carbon dioxide react with the coke, and this is going to help me form my carbon monoxide. So 2 steps it takes to create my carbon monoxide here. Okay, so industrially from the top here, you can see they throw the iron ore in and the coke in here at the top. Now, then the question is, okay, actually like that, then that's it, right? I got my molten iron already. It's good. But you realize that hematite actually contains your Fe2O3, but it also has other impurities such as your silicon dioxide, which is your sand. So I want to get rid of this, okay, so that my industrial process can keep carrying on. So what they do is they realize, oh, to remove that, I will need 2 steps. Okay, first step, when I throw limestone in, it's going to give me this main ingredient, which is called calcium oxide. So when I throw limestone in, because of the heat, the calcium carbonate will decompose to give me calcium oxide and carbon dioxide. This calcium oxide is what I want to remove my silicon dioxide. So you can see here, this reaction. These are the 2 main things that will react. Now, why is it so important? It's really because, why is this step so critical? It's really because, can you see, you are actually adding 2 solids to form your liquid over here. So calcium silicate, which is a slag, okay, molten slag, take note, typically we'll write the word molten slag, okay? Okay, so calcium oxide will react with my silicon dioxide to form my molten slag. How to remember the formula? I always tell my students, take note, it's called CaSiO3, okay, CaSiO, CaSiO3, okay, calcium silicate, which is known as your molten slag. So these are the 5 main steps that actually happen. So although there's labeled 4, but impurities being removed actually consists of 2 steps over here. Step 1 and step 2. Okay, 2 main steps for the impurities to be removed. These 5 steps, if you start from step 3, actually it's not difficult if you understand the whole flow of what's happening within the reaction itself. So for this whole blast furnace, you must remember the description. Sorry, let me use a different color. Right? You must remember the description. That's the first thing you must remember. How to describe each of the steps. Second thing you must remember is the chemical reaction. Chemical equation, okay, together with the state symbols. Okay, the state symbols are important because it gives you a greater appreciation of what each step is really talking about. And hence we are emphasizing a lot on the word molten and things like this. Okay, so this is the whole process of the blast furnace gone through quite quickly, okay, because it's really just memory work. I'm trying to make sense for you out of it to understand really what's happening. But you can read through the steps, it's actually not too difficult. Okay? Okay, the last point I'll highlight is this. Molten slag will run to the bottom of the furnace, but it floats on top. So we'll just read the first one and say, oh, molten slag at the bottom, sorry. So if I were to draw the whole, sorry, don't draw, it's on top. So if we were to apply this, what exactly are they trying to say here? Is like this. You realize this is slag. Slag is the layer on top. The iron is at the layer bottom. Okay, so molten slag is at the top layer because it is less dense. Molten iron is at the bottom because it is denser. Okay, so this is the idea of the blast furnace now. Okay, so we have gone through the whole blast furnace relatively quite quickly because it's really just a process that you have to take note. I'm just trying to help you make sense out of it. Okay, last one. Actually, last 2. Uses of steel, quite simple. Okay, I want you to just take note of this idea of what they call cast iron, okay, or pig iron. So now, this is actually just a follow-on process from your blast furnace. So after we get a molten iron, right? So the iron that's extracted from the blast furnace is actually known as your cast iron, or sometimes they'll call pig iron. Okay, it's actually not useful because it contains impurities. So what they need to do is they need to process it further. So how to process it further? They will actually, first thing, they will remove impurities in the cast iron. Okay, the steps, do take note, they're actually running oxygen through it to oxidize the impurities. Okay, then after that, they will react further with the silicon oxide to form slag. So realize as the reaction goes on, as they blow more oxygen, the iron actually becomes more refined, it becomes purer. Okay, more slags actually formed. Now, the molten metal left behind is actually pure iron. The term given to this pure iron is actually wrought iron. Okay, so this one a bit, take note of it. So cast iron is also the same idea as pig iron. After going through further impurities removal, okay, the pure iron, another term given to it is also called wrought iron. So please take note of the two terms here. Okay, once you got the pure iron ready, then I can mix with other things, okay, to form steel. Okay, they're just focusing on steel here. Okay, there's actually other kind of alloy from iron that you can make, but the focus here is actually on steel. Okay, sorry, other alloys. Okay, steel is the main one, but there's actually a few listed below. So if you look at this, right, there are different types of steels that can be created. It all depends on what other metals or what other things that's added to the iron. So if I just mainly mix iron and carbon, I'll get what we call the mild steel, or I can get what they call the high carbon steel. So you can think of low carbon steel versus high carbon. Now, please take note, when they say low carbon steel, right, it's actually just 0.25. High carbon is just more than 0.45. So it's actually mainly steel made of iron. But why do they want to create these two different steel is really because you realize for low carbon, it is hard, strong, and malleable. But the low carbon steel is hard, strong, and malleable, but the high carbon steel is actually brittle. So you can see the comparison over here. Okay, you can see the thing here. So question is, why not make everything low carbon steel instead of high carbon steel? Why not everything low? Why everything want to be why you want to make high? So key idea here is if I mix more carbon in the iron, okay, if I mix more iron in the carbon, do you realize that you will disrupt the arrangement more and actually makes it even stronger? Okay, that's why you realize it's used for boring tools, used for cutting. Okay, so it's actually quite an interesting idea behind this mild and high carbon, low carbon steel and the high carbon steel. Okay, what other types of steel you can get? You can get the alloy steel. So there's carbon steel, there's alloy steel. Alloy steel are two types that you are going to go more in depth into this. Okay, a bit more in depth. So there's the manganese steel and there's the stainless steel. Okay, so take note of what they are being used for. Okay, and what are their composition. Okay, I don't go further into this area. This one is just literally go and look through and try to remember it. Okay, this one you all can do it. Okay, the last part, rusting. This one primary school also learn already. So what's the key idea of rusting? Just take note, there are two main conditions. You need oxygen, which is found in air, and water. So oxygen and water are the two main things you need for rusting. Is that it? Actually, almost end of this chapter already. The key idea now is, how would they normally test you? Rusting, how can they test? So this investigation 14.2, please put a star here. This actually shows you what they would normally draw, or what does an experiment normally look like. Okay, so question is, distilled water, I know lah, this is water lah. Okay, good. But why must they use the word boiled? What's the difference? Why must they use the word boiled? So boiled actually tells you that they remove the air from the water. In this case here, I remove the oxygen. So when you boil the water, actually you are removing the oxygen away from the water. Then why must they put oil here? Is to prevent oxygen from dissolving into water. So this one, please take note of it. Okay. So boiling is to remove the oxygen from the water. Oil is to prevent oxygen from dissolving in the water. So you are trying to say in test tube A, this guy here is only nail plus water. No oxygen present. How about the second one? What is this? Anhydrous calcium chloride is to remove water. Okay, remove water or remove moisture. This cotton wool here is to absorb water droplets in case there are. So test tube B is actually just nail plus air. No water present. Okay. Test tube C, you realize distilled water, so got water, right? So it's a nail plus water, confirm have. There's no Oil, there's no boiling. So this one tells you all three conditions are there. Nail, water, air. Oh, sorry, I mean two conditions are there to make the nail rust. Then this one, wow, this one power. This one got three. Nail plus water plus air plus sodium chloride. So why must I do this? What's the purpose of this? So if you were to look at the results of this investigation, okay. Oh, sorry, they never tell you. I thought they were. Okay, maybe did they scan it? Oh no, I got pages missing. Okay, never mind. But this one, it will be the end. So I realized I forgot to scan the pages. So what is actually happening here is that you realize test tube D actually rusts the most. So what can you conclude from this is that the salt actually speed up rusting. Okay, this is the key point you must think back from here. Okay, nail without air, nail without water, this one, no rusting. So yeah, no rusting. And then lastly, this one, you realize this one rusting occurs. Right, rusting occurs. So this part here, the results actually tells you the how air and water plays a part in the rusting, plus also how the salt comes in to make rusting more serious. Okay. What I missed out in between here, sorry, actually missed out also, never mind, because in the last part, which is 14.7, this you just need to remember this. Okay, you just remember this in 14.7. Can? So 14.7, actually the key points, there's a lot of description here, but the main few that you must remember is actually already summarized in the key ideas. Okay, so by looking at the key ideas, you're fine, you'll be safe. Okay, so that's all for the chapter of metals. Yes, we have chonged through the whole thing, 2 chapters within 1.5 hours. Okay, let me stop the recording.